Hello and welcome today to this 4i lab and the process we are going to demonstrate for you is the rapid prototyping process. Okay. So let me just comment a little bit about what this rapid prototyping process is and how it helps in augmenting the industry, bringing into sort of micro features or micro parts. Okay. So the rapid prototyping is about sectional printing of material. It is also known as three-dimensional printing. The whole idea is that if there is any complex feature or shape as a CAD file which is available, the system tries to section that particular CAD file into small elements, okay? And each element is being deposited by means of plastics, which are typically two in kind. One is either polycarbonate or ABS plastic, and this particular machine has the capability of handling on the plastics. Although in the current domain of technology, there exist machines which also do the same with metals. Okay, so they are called fusion deposition modeling or metal fusion deposition systems, and they are used for non-strategic parts, particularly things like, let's say, coat hooks or aesthetic furnitures, etc., made up of metals. Okay, so the advantage behind 3D printing, this area is also known as layered manufacturing because you are manufacturing layer by layer. And the advantage behind such manufacturing processes is typically in terms of the saving of excess material that you otherwise incur in other contact machining processes where there is a lot of waste which is generated in forms of chips, okay, or even in other forming processes or associated, let's say, casting processes which are primary manufacturing processes. There is always a tendency of formulating a layer which is eventually removed. Okay. So in this particular application, the layer deposition process, the advantage is that such savings can happen in terms of obtaining a direct surface finish without performing any other machining process after this process has been done. There are several processes, there are several shapes and sizes which have been fabricated with rapid prototyping. This right here shows a part of a horse saddle. You can see this is a horse saddle. Okay. So here, for example, this actually is sort of the way that a person customizes his requirements for riding horses, etc. So everybody has a different physiological shape, and therefore it's needed that particularly something like a saddle should be able to customize to the particular user which is there. Okay. So not only the process is highly economical in terms of material saving, because you are just depositing rather than this is a material build-up process or I would say a surface machining process rather than a bulk process, which is subtractive in nature. Okay, so this material is an additive process. But apart from that, the main advantage of this process is that you can highly customize the parts or the features to the taste of the customer. And you can make very complex shapes which otherwise is not doable with these different machining techniques which are around. Okay. And in a way what happens is that once your CAD file is designed, irrespective of whatever is the complication which is involved, I'll just show you, for example, what I mean by complication. Okay, this is a crankshaft, okay, of an automotive. You can see the design and you can look into the kind of complexity which is involved in designing such process. Typically this is used in the automotive industry, and the way you generate it is in forming processes. But here you're basically depositing and making a scaled prototype or a model through which you can probably formulate the next step, okay, which can be used for die manufacturing for that forming process to happen. Okay. So one advantage of this kind of a process is because of the complexity of the shapes it can handle, it can be used as an intermediary for some of the primary manufacturing processes also. Okay. So in a nutshell, what I am trying to say here is that there are a lot of advantages associated with rapid prototyping. One of them is, of course, the high level of customization. Another is the ability to handle complex designs or parts. Third is a lot of material saving because it is a layered model and there is no secondary material which is wasted in the process. And then this can formulate an intermediate process for final primary manufacturing processes like forming or casting, where probably you have to do the mold development or you have to do the die making. So some kind of a prototype is needed, okay, in order to envision and design such a system. So having said that, the question comes how this layered deposition model works. So as I told you, the first step is about making a CAD file and sectioning the CAD file into slices or pieces. These slices could be close to about whatever the resolution of the equipment gives in this particular case. And as I told you, this machine handles two different equipments, that is ABS as well as PC. So for the ABS plastics, the minimum size of a slice which is available here is 125 micron, so 0.005 of an inch. Okay, and the basic raw material for this process comes as a roll. You can see this is a wire roll, okay, and this is what the basic raw material comes as. And this wire is fed from a very small nozzle which actually is able to move in a XY plane with the information that it would have, the coordinate positioned information which would have from the CAD file. So supposing now there is a sectioned layer of such a complex part. I showed you a part can be as complex as this. So probably I have made a small section of this somewhere here, and I am actually seeing what are the coordinates of that particular section and defining the tool path. So the nozzle would actually move in that path and try to maneuver itself by dispensing this particular plastic here by heating it up to its melting point. So the nozzle is typically heated at 300 degrees Celsius in this case, so that it melts the plastic, and then the plastic flows across the nozzle, and it's going and walking across a tool path which is generated into the overall feature size, and it is depositing that layer of 125 microns. So once this layer is complete, it is dried up, the next layer is deposited, and so next layer the information will again come from the CAD file on the basis of next slice which the CAD has originated on the basic file of the design of the drawing. So here is a very interesting technique. Let's look at the machine a little bit. Let us actually open this system up. So as you can see here, there are two parts basically of the machine. One is the controller part and also the material feeding part. The rolls are now currently in position and they are fed in the system, and the controller here is actually indicating several different aspects like what is the support material, what is the model, okay, and then there is a vacuum pressure and other pressures which are indicated. There is a small toggle switch here at the corner here, opening which would generate, a toggle switch would be operational here as I showed you only when the machine initializes itself. So there are several processes which are happening here after the controller has been switched on, and one of them is basically to auto home or auto position the dispenser unit or nozzle, okay, in the XYZ plane, and also it does several checks and balances at the beginning so that the machine can be completely initialized for the next run. Okay, so we'll have to wait for a little bit until the cursor here comes to unlock door, and at that point of time we can actually open the door. You see the light has been on inside the chamber where the rapid prototyping can actually happen. Okay, so the first stage of this machine would be related to setting up of this machine. We'll go back on the computer and try to make a CAD package and try to mesh it in a particular manner with all these specifications, where a file, a machinable file can be created for this system, and then this file would be transported in a soft manner into this system, and the machine path etc. would be predefined. So all what we need to do is to transport that file and then set this machine on and forget about it, so that the part can get manufactured inside this oven or the part containment which is there in the machine. So we want to now do this auto home, so we just need to enter for doing this command, and you can actually see now inside, if you have a look at it, the stage is going up, and there is a position of the nozzle with respect to the stage that is happening within this particular machine, okay, so that you can have a home position for the workpiece with respect to the nozzle, okay, within the machine system. So it is still homing XY gantry and the Z stage, okay, so this process will take a little more time. You can also actually see right on the top here is the dispensing nozzle which has come up, and it is now trying to position in the XY direction, okay, once the Z is defined by the workpiece, and then it will be all about the way that the nozzle will be dispensed and the correct tool path would be mapped as per the CAD slice, which would come inch by, or few hundred microns by few hundred microns as you construct the part, the final part. So the controller here, as you are seeing for the RP machine, after the homing of the XYZ has happened, stage has happened, shows a lot of options like build job, operator control, model status, maintenance, so on and so forth. Each of these has a certain meaning, and I will describe these along the way as we do the machining process. However, once we want to just actually first clear the stage with the existing whatever is lying inside, okay, from the last run, okay, and then basically try to prepare the stage for this particular run. So what we are wanting to do is to sort of go into this operator control, which is the second option here, which I can use the cursor key to go, okay, and then enter on this operator control, which takes me into another menu, sub-menu, which says unlock door, load, unload, so on and so forth. So I'm going to again enter because there's an unlock door option which is there, okay, and then it goes to another sub-menu where again there is a symbol unlock door here, okay, and I'm going to actually sort of start this, and this enters, or this actually is able to open the door. We cannot leave the temperature on for a long time because this actually is the sheet, the miler sheet, which was from the last run. I am going to remove this miler sheet and put our sheet here so that this becomes a new run actually of the process. The oven is actually getting heated up to about 119 degrees Celsius. Okay, so it's a little risky to actually at this stage touch the sample surface, but you have to just ensure that the sheet that you are posting is actually at the very corner, okay, of this particular thing, and there is a guide there which actually ensures that it is at the corner. Once it is done, you can close the door back, okay, so that now things are in place, and the next step that we want is to actually go back to the CAD software in the computer station and be able to process a particular file so that we can transport the file here in a soft manner and start and initialize the machining system. Okay, so basically now, as I told you in the last step, we demonstrated the machine. We said that it's really about a CAD file and how you can slice it into different pieces, which ultimately would define how the tool moves, or the tool path would be defined in that manner. So here, in this particular workstation, we would like to actually slice a CAD drawing into pieces. That is number one. Number two, there is a huge issue that supposing this is a part that we want to manufacture using RP. Now, we'll have to somehow suspend it in a manner using supports so that the whole part can be fabricated. And for doing that, the question is that how the support should be kept in a minimalistic manner, where later on that can be cleaved. There can be a parting line from which the main object can be separated from the support, and the support actually is the most hollow part with as less material as possible, okay, in comparison to the probably the object which is more solid in nature. So therefore, there has to be a provision associated with the machine where how to handle the part by keeping it at a certain inclination, or maybe keeping it parallel to the ground with some kind of an angle so that the whole part can be getting created, okay, and also about what are the dimensions, how the CAD file which has been designed earlier has to be transported, those issues have to be sort of catered. So today we are going to do the same. So with our FDM Titan machine that I showed in the last illustration, there are two different softwares which come with the system. One of them is called Insight, okay, and Insight version 9.1, which is actually used to define the layering, okay, and also define the tool path. So one issue is how to slice it into particular sections. Another issue, of course, is how to define the tool path. So both of these will be done in this manner. And then there is another software which is called the Control Center 9.1 version, which actually further illustrates how the object has to be placed in the overall miler sheet that had been shown in the last step. And if there are parallel objects to be placed, that how many objects would be there, which at a single go of the machine would be able to build up the job, etc. And you have to optimize the layout in a manner so that as many independent components can be developed together, that would typically give the yield of the process. Okay. So if the components are higher in that manner, the yield is also higher in a way. So that layout of the final placement of the jobs in the XYZ stage is given by the second software, Control Center. Okay. So we will do this later. The first version, of course, is the Insight, where we import and scan and try to section. Okay. And so let's look at how we handle it. This is the main screen of the software. So we actually go to the file menu, and in the file menu we actually can open up a file. So, here what I have done is, in the interest of time, I have actually made a CAD file earlier or borrowed it from some source, and typically this CAD data has to be saved as a .stl format for enablement of this Insight version 9.1 software to be able to read it. Okay, so therefore, the STL file has to be somehow opened using this Insight software. We open we go into this desktop, and then there is a folder which is there through a drop down menu. Okay, and then there is a crank final position. Okay, and there is a small part which is there, you will see, which we want to build using this system. Okay, so we open this file and transport this back to the scale. So, it is not scaled, we have to scale it because there is typically a confinement volume which would be defined by the bed size of the stage. I think I had mentioned it earlier that the bed size in the case of FDM Titan is about close to 16 inches times of 12 inches times of 14 inches. So, that is about the size of the biggest part that can be accommodated within this particular system. And I also defined that the minimum layer size that this system is able to resolve is about 125 microns. Okay. So, having said this, the parts appears to be in inches, and so it cannot be accommodated within this, and they are asking us to convert this STL into millimeters. Just for the sake of demonstration, we are going to do that this time because it is going to be a micro part. Also, it is going to give an illustration that how the microsystems can be fabricated using this particular method. Okay, so, we are going to select this model, and the model automatically is now translated and opened in the Insight version 9.1 software. Now, here there are different aspects which we need to consider for varying the different dimensions. So, this is not a very convenient way of locating the object, because naturally if you build the part like this, there is a tendency of the object to fall down or something like that. Okay. So, we want to actually locate it in a manner so that it is more convenient and we can very easily separate it from the remaining portion. And so, I am going to actually make the front portion of the part here as the bottom. Okay. So, I am going to actually now see what is the bottom. Okay. Take this up and then take this cursor all the way to this portion. So, this comes on the bottom and the part topples. Okay. So, now you can see the part has toppled and it has lied down on a flat surface, which is actually more appropriate for the purpose of doing RP or rapid prototyping. Okay. So, now there are these questions of what is the slice height, etc., like, for which I would like to set up this system. So, for slicing it, the first thing we need to control here is actually to do the machine setup. Okay. And you basically try to configure the modeler here in a manner so that you can define what is the layer thickness, etc., and what is the nozzle that you have to choose. We have to remember that there are about 4 nozzles in this system which has been delivered or specified by the manufacturer, and they are classified as 4 different types, starting from T12, T10, T12, T16 and T20. Each of them has a different orifice diameter, because ultimately if your slice height has to be more, naturally the dispensing rate also has to be more for the tool to actually be able to carve the object out. So, if the nozzle is slightly higher in diameter, in that case the dispensing would be faster, and therefore it can go to a higher layer thickness. Okay. So, it all is defined by that layer thickness, that how the nozzle selection, etc., to take place. Typically there are 2 different materials, as I told you earlier, that this equipment can handle. One is polycarbonate, another is ABS plastic. So, when you are talking about ABS, there are different layer thicknesses even which are available. Okay. And there are all the nozzles, including T10, 12, 16 and 20, all the grades of the nozzles are being used in that category. In the case of polycarbonate, system is a little less flexible, so there are only 2 layer thicknesses which are able to get catered, and one of them is about 0.01 of an inch, and another is about 0.07 of an inch, and there are only 2 different nozzle sizes which has to be used. So, in this particular drop down menu, you can see there are different aspects given here. The first is called the modular type. So, let us actually see there are different machines which the manufacturer has. So, typically ours is a FDM Titan T1. So, we have to do this as a selection. Incidentally, this is also set as a default selection in the software. So, you need not worry about it. You can keep that as the default value which the software takes. There are different materials again. So, in this case it is polycarbonate, but there are ABS materials, there are variety of different even polycarbonates, okay, which are available. In this case we want to choose a simple polycarbonate PC. Okay, so it is demarcated by PC. So, we are going to take this up. Okay. Now, model automatically the model material color is defined as white in this case, and then the question of support material comes. So as I told you that if there is a complex shape like this and you want to position it over a certain surface, you have to give a support to get it standing. So most of it is in air, and you can actually build by using layer by layer fabrication approach. Okay. And the support is very critical because this is a wasted material. Later on you have to remove this material, and the material would be removed as if it is a parting line and it is coming out of that. Okay. So here in this particular case you can see the support material being defined by on the polycarbonate. So the option that is being set up in the software is that if there is a PC part, typically the support will also be of the PC. Okay. So the PC support is defined here, although you can change it probably by going into the the setup of the software, but at this time we want the material to be same, so we are selecting PC support. Then if you want to really invert any build materials, the answer, yeah, we don't want to do the invert build material option. Cut. So the invert build of material option actually is particularly when there are more than one materials to be selected. Unfortunately, our machine is not capable of handling this option or selection of multiple materials. And particularly if you want to deposit something which is like a layer by layer of 2 different polymeric structures or maybe 3 different polymeric structures, the option of invert would come in more handle. There is a slice height option which is kept here. Now you can see there are 2 different slice heights. One is 0.007 of an inch and one is 0.01 of an inch, which makes this about close to about 250 microns. Okay. We want to select the thicker slice height because in the interest of time we want to complete this fabrication process earlier. So we are going to build this slice 250 micron by 250 micron. One layer would be 250 micron, and that's how the whole slicing would be done in the Insight package. Okay, so it's essentially a slicer package of a CAD file that we are talking about. And automatically, if you see that if you select this 0.01 option, automatically T16 nozzle is selected, which means that this would be able to handle and dispense the 250 microns layer. So T16 is probably a slightly thicker in diameter nozzle which is existing in this particular case. If you had selected 0.007 as given earlier here, then you will automatically see that T12 is being selected automatically. That means a lower size orifice nozzle is selected in that particular case. So it is very obvious that the software is quite friendly. It will minimally work in a manner so that it actually tailors all these systems. Finally, we make it okay by pressing on this right button here. So now you can see the text box which comes here on the top is mentioning FDM Titan T1, slice height of 0.01, model of T16 tip to be used, a polycarbonate part and a polycarbonate support. All these options have come here, which shows that the machine has now accepted the various different options associated with this system. Now the question of slicing comes into picture, and I would just like to illustrate a little more of how the component is placed, and the styling, how the styling would be happening. So you have different options here on the right side of this particular system. You can see there is a part interior style. Okay, and if I just click down on this drop down menu, there are 3 different options, namely solid normal, sparse and sparse double dense. Okay. So what it means essentially is there are 2 different options this machine has. One is that it has a honeycomb layout structure, which is sort of a lesser density structure, and then there is a flat plate structure which is there. So the tool may move in like a honeycomb manner. The tool may also move in like a layer by layer. Okay. And the solid normal would mean that we want the bulk to be equally dense, okay, and it may be depositing layer by layer, or maybe even the tool path, even if it is like a honeycomb like structure, would be so close to each other that they would be considered to be one whole. Okay, so this is the densest form which is available. There are different other options which are there, namely sparse, which would mean that this is typically sparse when you talk about supports, etc., where very less amount of material is deposited and the gap between the materials are very high. So it is like a packet of cardboard, a corrugated cardboard, okay, where there is a honeycomb kind structure and then there are 2 layers which are giving the toughness or the strength to the whole sheet. So support can easily be done in that manner because support is not to be used for any future applications. The support is only temporary sort of dismantleable structure, which is only because you want to support the object to its place to build it. Okay. So you can actually in this particular case select the solid normal because it is a real part, it is a crank, and we are selecting the densest, And then you have a visible surface style. So there are two different, one is normal and another is enhanced. So we will select the enhanced option here, which meaning that the surface would be quite integrated and the surface would have very good topology. Okay. There is a support style again. The support style can be just basic support or a smart support. So let me just illustrate what it means a little bit. Supposing there is a object like this and you want to place it on a certain angle, okay, in order for the RP system to build it layer by layer. When it does it, there is a question of support which comes into picture. So one support can be just simply orthogonally placed like this. Another support can be at a certain angle which is able to still support the weight of this guy, because you will have to calculate when the CG of this person or the CG of this particular object is within the periphery of the support. Okay. So if supposing the CG is within that support, then it will not topple. And that is the basic idea, that you don't want the part to be toppled while it is being made. So you can skeletonize the support material in a manner so that it can do its job by at a certain angle also. Okay. So this is called a smart support, which actually saves the material. So one option could be to just give a thick grill like this in a perpendicular manner. Another can be to go like this, make a certain base size, and then from there go at an angle and be able to support it, so that the overall CG is still within that base material. Okay. So this is the way that the support is designed. I think you probably understand philosophically how the support would be able to manage, and the idea is the support should be minimalistic as possible. So in this case we will do the smart support. So we will actually select the smart option here. Okay, so automatically the software will calculate that the support is not much of the material, okay, wasted. And then of course you have a system mode, which again is fine system and the normal. So we will select the fine option, because the system has to do a good job in making the integrated surface quality of this part by depositions. And we are kind of done at this level by setting up all the parameters for the slicing. So let's look at how the slicing happens. So if I press this option right here, you can see that the system slice is available now. You can actually go up and you can see each individual slice being made in the software. So each slice has now a thickness of about 250 microns. That's the beauty of this whole process. Okay. And what I would also like to illustrate here is that once this slicing is made, you can actually also look at the independent slices by these options here on the left corner, where you can go from the top end, okay, and then with the page up, page down option, you can actually keep on varying this and see what are the various layers which you have to deposit. And in fact, this also mentions what is the tool path to deposit that layer. Okay, and finally you will see that the whole surface is being constructed based on that. Okay, and then you can also do it simultaneously from the top surface as well. And you can go up by doing the page up, okay, in a similar manner, and that's how typically you get all the support. So here again, coming back to the same option, I can just there is a option here with all slices shown together in a patch, which will reinstate back the whole sample or the piece, okay, in the system. And so therefore this is how tentatively you can look at the slice plot. So once the slice plot is done, and the question of defining the tool path comes into picture. So the other option now we have, once we have actually done the slicing, we have to create a support system here. There are certain holes, etc., which you are not able to see because of the intense slicing, but you can see there are certain holes, etc., which has to be created. Okay, and therefore there has to be a support within them, where typically the density would vary, etc., and there can be easy cleavage. Okay, so that the support can be later on taken off to create that hole in that particular dense structure. So having said that, let us actually go to this other option here which says support. So create support for the current job. So I am going to just press click on this, and now the software is going to create supports here. So here you can see that there are these yellow lines which are actually reflecting what are the support media which is there. There are these supports which are made here, the supports which are made on the periphery of the object, okay, something like this. So you have built up the supports here, and then finally we want to actually find out that within one such section, what is the tool path which is getting created. And the tool path is reflected by this green symbol, which is actually reflecting the zigzag motion of the tool path within such a domain. And I want to create the auto tool path. So the software actually now tries to compute and create a layer by layer tool path. So that you can easily look at by going to the various layers, how the tool paths are varying, and you can see that how the different layers have been, the green actually represents the tool path. So you can see that how the different layers are having a certain tool path defined where the nozzle would actually do the dispensing action. Okay. And typically that is how the whole system is based on. So this is typically the support structure. As you can see, it is much lesser in terms of the density of the material, because it will be like a honeycomb kind of a structure. The distance between the two dispensing points would be much more, okay, in that, because this is something which is in any event going to be sacrificially removed, and the material has to be as low dense as possible, so that we can make lesser losses than is possible. So therefore, this is how actually the whole system is made. So let me just recall what all steps we did it. We opened a CAD file in the .stl, available in the .stl format. Then we tried to size it down to the volume of the box, which is 16 times or 14 times of 16 inches cube in our system FDM Titan. After doing this fitment of the component within the volume of the box, we did various options to it. First of all, we tried to define the material. We wanted to define the slice height, okay, and the tip size. These things were selected. Once that was selected, then we are kind of ready with the next step, which is the slicing option. So we go to the slicer command or slicer menu, okay, and then slice it into these 250 microns. You can see the slice slot coming out by going to the logo here in the top left corner, which says from top to bottom you can actually look at various slices, see if they are interfering with each other, is there a problem in the toolpath, etc., in the slice, etc. And normally there is no such problem, because the software is a highly error free slicer which has been developed. And then you can also give the various material texturing or patterning by mentioning whether it is a solid normal or whether it is a sparse or sparse double dense kind of a layout, which automatically means that you may vary the densities of various zones, making it corrugated in some places and uncorrugated if you need. Here in this case, we wanted the whole model to be made out of a solid block with uniform strength all through, so we have chosen the solid normal. Okay. We also talk about the visible surface style and also the finish with which the machine would deposit, and also give a support style which would save off the material. Remember, we did the smart style in this case, which would allow the material to be minimalistic for doing the supporting action of the component. So once all these things are defined, we then try to see the or give the support structure of the material, and once the support structure is also defined, then we do the tool path. So once the tool path is planned, as you saw that the material had a denser tool path than the support structure, which means that the support was much less material, just only intended to support the material of which would be parted away later in a non-useful material. Once this is done, the file is complete. We can save this file, looking at the complete illustration here, okay, and save it, and going to the save option here. So when we save the current job, it will automatically be saved off at the same place, okay, just this new folder, the same location, just beneath the file that was initially extracted as a .stl file, okay. And so therefore, we will just save this here. Of course, there is some overwriting existing job in the same name. We have to just do that overwriting here, so that the job is now saved as a .cmb file, which would be later on able to get extracted by the other version of the software, which I actually told you at the beginning was this control center, okay. And this control center is a software which would now fire particularly the job all the way to the tool. So before starting this also, I would just like to sort of do some settings in the internet protocol, because this machine here, the computer, is connected to the FDM Titan through a certain LAN protocol, okay, and this LAN protocol has to be initiated for this particular PC. So what I am going to do is to actually go all the way to the network connections here, okay, open the network, open network sharing center, and then go all the way to the local area connection network here, and then enable or disable certain properties, okay. So what I am going to do is to go into the properties here and select this Internet Protocol version 4, by virtue of which it is being set. So we see the properties here. You can see the machine is preset in the IP address 172.28.21.42. This is the IP address of the machine. So this protocol has to be initially defined, so that you can, whatever you do in the CC the control center here would automatically be operated online, or it will be sent online to the FDM Titan. And once we do, or once we are through all this process, we'll again go back to the machine and see how this job, which now got queued up in the machine server or the machine's controller, would be able to do the printing, the 3D printing in the machine itself. So here again the system is very easy. We just insert the particular CMB file by opening the crank final, which had done before. So this is selecting this particular file. So when we open it now, you can see the crank final file has been placed exactly at the center stage, okay, of the FDM Titan. So you may decide to make several versions of this copy, or put different parts together, or lay out, in a conducive manner, so that you have the whole area being exploited. You remember, every time the tool has to deposit, it has to go back to its 0 position or home position. So it is a better idea to do parallel processing by parallelly printing many parts together. And so here the idea is to be able to sort of take this feature and make something where you can have multiple of these features, okay, together. So you can actually make a copy of the same, okay. So you can make a copy, and you can say that you want 3 copies, so the same thing would be copied like this, okay, and then you can place it one by one, if you want to do that way, so that you have many of such items. If you had multiple items in general, I mean all the parts may be different parts also, you can place like this and make an array. Okay, so the purpose of this control center really is to make minimalistic effort on the part of the dispensing unit there within the FDM Titan, so that maximum printing can be done in this stage altogether. Okay, so it makes it from a serial to a parallel process essentially. So once this is done, I would just like to sort of remove some of the things that I had made. I just want to print only one for the sake of clarity, okay. And you can actually rotate it, invert it, you can actually select this particular part here, and you can rotate to any particular direction, okay. I would just like to prefer the orthogonal direction here in the interest of the printing, so that the tool path is saved for quite some time. Every time it positions back to the XYZ is a lot of work for the tool as well, okay. So once this is done, I think I would just like to build the job, okay, and there is a build job menu which is here. So the moment I click it, the job is now almost ready, okay, and you can see probably that the job is in the queue already, okay. So you can see that there is a pack/crank final admin, okay, which has actually been started at 15:02 hours on today's date, that is 18/9/2014, and the estimated build time is given here to be about 47 minutes. Also, what is important for us to look is that what is the machine loading at this time. So you already saw the material confinement. I am going to illustrate this again, that there are these material canisters which are the initial raw materials, those wires which you have to feed in. So there is actually a calculation done by the machine itself which talks about how much amount of material is left here, which is about 86 inches cube, okay, in the model canister. And the support canister has a material of about 37 inches cube. And the amount of model and the support materials which are needed are also mentioned here as 0.407 inches cube and 0.038 inches cube. So typically you have to understand that these two which are needed should be lower than the material which is available. Okay. So once this condition is met, I think we are all set to do the machining operation, which we will see in the next illustration. So here now, you can also in this software, after looking at the queue, you can look at the systems view, which gives you an idea of the time. This is going to take about 47 minutes. So the position here really shows the start time. It's about 2:10 right now in the day. So you can actually get this. So it's going to start at 2:10 and complete at about close to somewhere beyond 3, something like that. Now, because there is going to be a heating time, there is going to be a cooling time. The actual printing time is about 47 minutes, but there is going to be a pre-processing time which is needed for the controller to be set in, so that the total time duration that the whole job would take is near about close to 340. So it's about an hour from which the job would be finished. So all these details can be described on this particular system. It's very helpful for the user, so that he can actually process and plan how much time the machine will operate and when it needs to be done. So once this is done, I think I will just simply close this particular software, and we are now machine able to go to the workstation. And so basically now, I'd just like to demonstrate what happens in the controller of the machine. The sliced part has already come and it has been queued online to this machine here. If you just look into the controller, the screen right here says build job. Okay, so there is an option called build job. Down here are a set of keys where there are different controls which are available. If you want to escape from a certain command, you just press this escape button. If you want to go into the command, you just press enter button, and then you can actually go up and down with these cursor arrows, and then needful would be done in terms of parameter setting later on. Okay. So we just enter the build job menu. So once we do that, you can see that they're talking about build next job, and then they are saying crank final. So this is the job which has been queued to the machine. I'm going to build this job now, and the moment I press the menu key here, you will see that first the stage would go all the way to the initial position, and also there would be a setting of that dispenser nozzle to one corner, which is the home position for the nozzle, from where the printing would start to take place. So I need to just do this build next job e crank final. The moment I enter it, now they are saying need all 4 canisters present. So the job can be done by 2 canisters, because as you saw that the PC support material as well as the normal PC which was there was having volume wise much larger volume in comparison to the need which was there to develop this particular job. So I just go to the continue option here and just bypass this. So now you can see that inside the machine cabinet you have the auto positioning of the dispenser tip, and then slowly the stage is coming up all the way to the point when the initial dispensing will start. One thing which is very clear here is that the tip has gone to its home position, and we had also defined our job in that particular pocket only, so that there is not much motion of the dispenser to be made with respect to the stage. So once it is all set up, there is an option here which says demo bounding box. Okay. So if you go back to this particular controller here, you see there is an option which says demo bounding box. All it means is that when I am going to press this demo bounding box, it will show the domain within which the printing has to be done on the surface of the 3D printer. Okay, so I am going to just select this particular operation here, do the enter, and you can see that there is a domain the tool path has gone inside. So the domain which the tool path has gone inside, the moment I enter demo on the, you can see that there is a square domain which the tool dispenser is going. This is kind of the domain where the workpiece printing would be actually done. So now I just continue it. So go to the next option and continue and enter it, and now the whole auto calibration activity in the machine would be in automatic mode, and the whole printing would start happening. Okay, where there would be a dispensing and writing of the particular shape on a slice by slice, okay, on the Mylar transparency film.